Hi, I am Tanvir Arifin from Morgan State University. Today I am going to present our recent work titled Voltage over Scaling Based Lightweight Authentication for IoT Security. My co-author. As I mentioned, this work is focused on device authentication techniques in the Internet of Things ecosystem. We are living in an increasingly interconnected world. The advent of Internet of Things is ushering the era of smart systems, from smart sensors to smart power grid. IoT connects a variety of things or objects to the Internet through a network of computers, sensors, databases, and other electric components. The number of IoT devices worldwide has grown from 15.4. As more and more devices are connected to the Internet, they will interact and share data. Secure key storage and device authentication are two key techniques that will assure that data is communicated and shared between trusted and authenticated entities. Traditionally, key generation and device authentication protocols are based on classical cryptography. This requires expensive secret key storage and complex algorithms. Unfortunately, in many IoT applications, resources like CPU, memory, and battery power are limited and cannot afford such classical cryptographic security solutions. Therefore, lightweight solutions for IoT security are imperative to develop a network of trusted devices. So to address this issue, physically unclonable functions or PUFs are proposed as device authentication solution. PUFs exploit uncontrollable process variations during the chip manufacturing process to generate unclonable responses. Based on the number of generated challenge response pairs, it can be broadly categorized into weak PUFs and strong PUFs. Weak PUFs can be used as unique keys or seeds for traditional encryption system. On the other hand, strong PUFs can provide a huge number of unique challenge response pairs to authenticate a device. VOLLA uses voltage overscaling techniques to generate device fingerprints. Voltage overscaling is a common power reduction technique in approximate computing. As we all know, dynamic power consumption in a digital circuit decreases quadratically with supply voltage. Also, the delay of the circuit increases dramatically with lowering supply voltage. With correct timing constraints, the circuit produces correct output for all input. However, when the operating voltage is lowered, the timing violation will incur errors in calculation. Furthermore, the errors produced by the process variation are random and can be reproduced by original device, but it would be difficult to clone. Therefore, the errors can be used as hardware fingerprints for authenticating devices. For example, we can see that it is very easy to generate voltage overscaling errors in long chains such as ripple carry adders that have a long signal transmission delay. So if we use two different ripple carry adders, then at a voltage below the critical voltage for computation, we will see process variation dependent signature. Here we provide an illustrative example. First, we use a non-voltage overscale adder to add two images and generate this figure A. Then we use two voltage overscale adder and try to generate the same image. As we try to do that, we can see that under voltage overscaling, we have process variation dependent noise pattern or error patterns in the resulting images B and C. Images D and E shows the difference between the image A and B and A and C, and the image F shows the difference between the image B and C. from the noise pattern or the error pattern, we can definitely see that the process variation dependent errors are present in voltage overscaled computation. Based on this idea, we propose VOLTA. VOLTA is a two-factor authentication scheme where the two factors include a secret key K and an adder that generates error under voltage overscaling. The top figure here shows the authentication protocol for VOLTA. An example calculation for VOLTA is illustrated in the figure below. Here, if we look into this bottom figure, we can see the process flow for different challenge response pairs. If we notice that in the horizontal case, these responses are different for each different challenges. However, if we look into the vertical data, we can see that this data for some bits remains the same over different challenges. Based on this inspection, we can build a machine learning model to model this adder and attack on this voltage overscaling based authentication scheme. So we decompose Volta's working process into this AND, OR, and NOT gates and model the logic gates mathematically. These basic gates can be expressed as mathematical formula as shown in the top table. We then further design the attack model for VOLTA as shown in the bottom figure, where we represent this 8-bit ripple carry adder with a neural network model. In VOLTA, the current input is combined with the previous input to create the actual input. Therefore, since the current output of VOLTA is related to the current input and previous input, we see that a typical recurrent neural network or RNN model can be very beneficial in modeling such computation. Therefore, we present here the complete RNN model for attacking VOLTA. So the modeling attack actually works on VOLTA because the errors that is generated by the voltage overscaled adder, they are related to the input timing, and the current output is generated by current input and previous input. However, if the correlation amongst this input is enhanced, or if the input is obfuscated, such machine learning attacks would be difficult. So the key idea of this updated algorithm that we present in this paper is to combine the previous input with secret keys and random numbers to generate a dynamic new keys in the VOLTA authentication process. We use these dynamic new keys to obfuscate the current input. We call this protocol as challenge self-obfuscation structure, or CSoS. So in CSoS, we have this previous input, we combine the previous input with secret keys and random numbers, and we generate dynamic new keys and exploit these new keys to obfuscate current input. Based on these key ideas, we present this CSoS-based ML attack resistant authentication protocol for VOLTA. Here the key and the voltage, the key K and the VOS adder are used to authenticate the devices. In this protocol, the key consists of three different keys, K1, K2, and K3, where K1 and K2 are used to obfuscate the challenge in CSoS, and K3 has two. As the CSoS computation needs some temporary storage during this process, we design a CSoS-specific hardware component. We call it input cache structure that can store some temporary bits. Here, this is the complete hardware implementation for CSoS-based VOLLA designs. We can see that this architecture not only supports 8-bit or ripple carry adders in voltage over scale systems, it can also support 64-bit Arbiter PUFs with weak PUFs configuration, or it can also support 64-bit Arbiter PUFs with strong PUFs configuration with TRNGs. Now we look into the experimental results of our paper. As discussed before, we find that machine learning attacks are really successful on VOLLA. For example, we can see that on the left figure that if we use these recurrent neural networks and if we use Hamming distance to evaluate the modeling accuracy, we can see that when only 1 byte of the current input as is used for the training input, the prediction accuracy of this network becomes 91.54%. If we use 10 consecutive bytes of input for training, our accuracy goes up to 99.65%. Also, on the other hand, as we increase the number of training data, we can see that with about 10,000 training data, we can successfully attack VOLLA. On the other hand, the effectiveness of CSoS-based machine learning attack-resistant authentication is evaluated in this slide. We can see that even with these recurrent neural networks and large number of training data and a large number of input sequences, the prediction accuracy of recurrent RNN-based models on VOLLA remains lower than 52%. On the other hand, even if we increase the number of iterations, the prediction accuracy still remains low. Therefore, this CSoS architecture can create resistance to learning attacks for VOLLA. We have also evaluated the effectiveness of CSoS architecture for defending Arbiter PUF against machine learning attack. We can see that even with a large number of training data, these CSoS-based Arbiter PUF are showing a prediction accuracy of less than 60% for machine learning attacks. On the other hand, the original Arbiter PUF can be easily broken with as the number of training data approaches 10,000 or higher. The same thing are also shown for strong PUFs, and we can see that CSoS makes strong PUFs, the prediction accuracy for strong PUFs for in these machine learning attacks and under 60%. Now let's talk about the hardware overhead due to the CSoS design. From the data in the table, we can see that the hardware overhead for a 64-bit CSoS-based Arbiter PUF is not much different from a 64-bit 3 XOR PUF. Also, on the same time, if we evaluate the power consumption, it can be seen that the power consumption of the proposed structure is a little larger than 3 XOR PUF. However, we used artificial neural networks to model 3 PUFs, and with 100,000 challenge response pairs, we can see that artificial neural networks can achieve up to 99% accuracy for non-CSoS based design. However, it only achieves up to 52% modeling accuracy for on CSoS based design. So overall, although we have a slightly larger power consumption, we can see that these designs can effectively so in conclusion, in this work we demonstrate that machine learning attacks such as artificial neural network, recurrent neural network can break VOLLA-based authentication schemes. Specifically, the prediction accuracy for recurrent neural network goes up to 99.65%. Based on our understanding, we proposed a CSoS-based machine learning resistant authentication protocol that reduces the prediction accuracy of modeling to less than 51.2%. CSoS is not only efficient for VOLLA, but it can also be deployed for strong PUFs and exhibit good obfuscation ability. After deploying this technique to model, the modeling accuracy for Arbiter PUF goes below 54% with state-of-the-art machine learning attacks. So overall, we hope, thank you.